Polyphase induction motors. Induction motor is singly excited AC machine. Its stator winding is directly connected to AC source, whereas its rotor winding receives its energy from stator by means of induction. Types of induction motors. Rotors. Squirrel cage rotor consists of a cylindrical laminated core with slots nearly parallel to the shaft axis or skewed. You can say skewed. Each slot contains an uninsulated bar conductor of aluminum or copper. At each end of the rotor bar conductors are short circuited by heavy end rings of the same material. Wound rotor or slip ring rotor consists of slotted armature. Insulated conductors are put in the slots and connected to form a three-phase double-layer distributed winding similar to stator winding. The open ends of the star circuit are brought outside the rotor and connected to three insulated slip rings. Cage rotor is cheaper, requires less maintenance, and have higher efficiency and higher power factor than wound rotors. Next heading, production of rotating magnetic field in three-phase system. In a three-phase balancing winding is excited by three-phase balance current. A resultant MMF or flux is produced of constant magnitude of 3 by 2 Fm, 3 Fm by 2 or 3 phi m by 2 in the air gap of motor and rotate in space at synchronous speed ns. The direction of rotation of resulting flux in the air gap depends upon the phase sequence. Resultant MMF can be given as Fr equal to 3 Fm cos omega t minus theta whole by 2, where Fr means resultant MMF, Fm means maximum MMF. Speed and slip, synchronous speed ns equal to 120 F by P, where F means supply frequency, P means number of poles. Slip S equal to ns minus nr whole by ns. Numerator ns minus nr by ns, where ns means synchronous speed, rpm, nr means rotor speed, rpm, rotor frequency, fs, f2 equal to sf1, f1 means line frequency. Speed of stator with respect to stator, speed of stator field with respect to stator equal to ns. Speed of rotor field with respect to stator equal to ns. Speed of rotor with respect to stator equal to nr. Speed of stator field with respect to rotor equal to ns minus nr. Speed of rotor field with respect to rotor equal to s into ns. Relative speed between rotor field and stator field is 0. Rotor speed nr equal to 1 minus s into ns. Rotor of induction motor never runs at synchronous speed nr less than ns, otherwise induced EMF in rotor equal to 0. Per phase induced EMF in stator winding E1 equal to root 2 pi n1 f1 phi k omega 1. In rotor winding at standstill E2 equal to root 2 pi n2 f1 phi k omega 2. K base omega 2. Okay na, root 2 pi n2 f1 phi k antam. K కింద బేస్ లో omega 2 at any slip s E2 equal to root 2 pi n2 of sf1 phi k omega 2, or k omega 1. K omega 2 means winding factors of stator and rotor windings respectively, n1 n2 number of turns of stator and rotor winding respectively. Rotor EMF, current and power. Per phase rotor current at any slip s I2 equal to E2 whole by root over R2 by S whole square plus X2 square. R2 by S and is separate to plus X2 square and is separate. So I2 equal to E2 by root over R2 by S whole square plus X2 square. The circuit is JX2 in series with R2 by S. R2 by S is a stator. Nothing but R2 by S is nothing but adjustable resistance. R2 means rotor resistance at standstill. X2 means rotor leakage reactance at standstill. U2 means per phase value of induced EMF at standstill. That is standstill. Rotor power factor. Rotor current I2 lags the rotor voltage E2 by an angle theta 2. Theta 2 equal tan inverse of Sx2 by R2. tan inverse of అనేది యాంగిల్ ఏమొస్తుందంటే sx2 by r2 రోటార్ పవర్ ఫ్యాక్టర్ ఈక్వల్ టు cos theta 2 per phase power input to rotor pg equal to e2 i2 cos theta 2 that equal to i2 square rs by r2 by s. pg is the power transferred from stator to rotor across the air gap, also called air gap power. Rotor ohmic loss equal to i2 square r2 equal to spg. Internal mechanical power developed in rotor pm equal to 1 minus s into pg. Internal gross torque developed per phase T equal to internal mechanical power developed in rotor whole by rotor speed in mechanical radians per second. T equal to Pg by omega s that equal to Pm by omega r that equal to rotor ohmic loss by omega s into slip. Omega s into slip is the denominator part, rotor ohmic loss is the numerator part, where omega s omega r means synchronous speed and rotor speed in mechanical radians per second. Output or shaft power PSH equal to Pm minus mechanical losses, PSH equal to Pg minus rotor ohmic losses minus mechanical losses. Friction and windage losses are the mechanical losses. Output or shaft torque TSH equal to PSH by rotor speed that equal to PSH by 1 minus s into omega s. 1 minus s into omega s is the denominator part. Air gap power Pg equal to stator power input minus stator I square r losses minus stator core loss minus stator core loss. Power flow diagram. Power flow diagram. Input power minus stator copper loss plus core loss gives rotor input PG. Rotor input PG నుంచి minus rotor copper loss plus rotor core loss ఇవి మొత్తం సబ్స్ట్రాక్ట్ చేస్తే వచ్చేదే మెకానికల్ పవర్ డెవలప్ పిఎం. ఆ మెకానికల్ పవర్ డెవలప్ పిఎం నుంచి రొటేషనల్ లాసెస్ సబ్స్ట్రాక్ట్ చేస్తే నెట్ అవుట్పుట్ పవర్ పిఎస్హెచ్ ఆర్ షాఫ్ట్ పవర్. Efficiency of 3-phase induction motor eta equal to PSH by PSH plus PF plus POH into 100. PSH means shaft power, PF means fixed losses that equal to core loss plus friction and windage losses. POH means stator and rotor ohmic losses. Equivalent circuit, exact equivalent circuit referred to stator. R1 JX1, RC JX5, RC JX5 అనేది parallel ఉంటుంది. JX2 dash R2 dash R2 dash into 1 by s minus 1. Transformation ratio A equal to E1 by E2 equal to effective number of stator series turns per phase N1 dash whole by effective number of rotor series turns per phase N2 dash. Per phase generated EMF in rotor circuit referred to stator side E2 dash equal to A into E2. Per phase rotor current referred to stator side I2 dash equal to I2 by A. Per phase rotor resistance referred to stator side R2 dash equal to A square R2. Per phase rotor leakage reactance referred to stator side X2 dash equal to A square X2, where R1 R2 means per phase stator and rotor resistances, X1 X2 per phase stator and rotor leakage reactances at standstill. Analysis of the equivalent circuits. All the rotor quantities have been referred to stator side. Okay na, R1 JX1 JX5 I2 dash JX2 dash R2 dash by S. Thevenin's equivalent circuit RTH JXTH JX2 dash R2 dash by S. Thevenin's voltage across A and B, VTH equal to V1 into JX5, that is the numerator part, denominator small r1 plus J into small x1 plus x5, J of x1 plus J of x5. Okay na. Thevenin's equivalent impedance across points A and B, ZTH equal to R1 plus JX1 into JX5 whole by R1 plus J of x1 plus x5, that equal to RTH plus JXTH. Thevenin's equivalent resistance and reactance across points A and B, neglecting R1 as R1 is far less than x1 plus x5, RTH equal to R1 x5 by x and XTH equal to x1 x5 by x, where x5 is magnetizing reactance, V1 is stator applied voltage, capital X equal to x1 plus capital X5, total torque TE equal to KT by KT whole by RTH plus R2 dash by S whole square plus x1 square into R2 dash by S. KT numerator part చెప్పేస్తా చూడు, KT into R2 dash, denominator part RTH plus R2 dash by S whole square plus x1 square into S Newton meter, where KT means 3 V Thevenin square by omega S and x1 means x2 dash plus XTH. maximum internal torque TERN equal to KT by 2 into RTH plus root over RTH square plus x1 square Newton meters. Maximum internal torque is also referred as stalling torque, pull-out torque or breakdown torque. Slip at maximum torque SMT equal to small r2 dash whole by root over RTH square plus x1 square. Starting torque TEST equal to K2 into KT into r2 dash whole by RTH plus r2 dash whole square plus x1 square. RTH plus r2 dash whole square plus x1 square is the denominator part. Motor torque in terms of maximum torque TE equal to 2 into TEM whole by SMT by S plus S by SMT. Total mechanical power developed PM equal to 3V Thevenin square whole by RTH plus R2 dash plus R2 dash into 1 minus S by S into full whole square. అంటే అక్కడ నుంచి R2H plus R2 dash plus R2 dash into 1 minus S by S whole square plus x1 square. ఇదంతా సెపరేట్ ఇంటూ R2 dash into 1 minus S by S. R2 dash of 1 minus S by S. Slip at maximum power SMP equal to R2 dash by root over RTH plus R2 dash whole square plus x1 square plus R2 dash. రూట్ ఓవర్ ఏమైనా వస్తుందంటే ఆర్టీహెచ్ ప్లస్ ఆర్2 డాష్ హోల్ స్క్వేర్ ప్లస్ x1 స్క్వేర్ మాత్రమే రూట్ వచ్చి దాని సెపరేట్న ప్లస్ R2 డాష్ స్మాల్ R2 డాష్. స్లిప్ ఎట్ మ్యాక్సిమం పర్ ఎస్ఎంపీ ఈక్వల్ టు R2 డాష్ బై రూట్ ఓవర్ ఆర్టీహెచ్ ప్లస్ R2 డాష్ హోల్ స్క్వేర్ ప్లస్ x1 స్క్వేర్ ప్లస్ R2 డాష్. మ్యాక్సిమం పవర్ పిఎం మ్యాక్స్ ఈక్వల్ టు 3V Thevenin స్క్వేర్ హోల్ బై 2 ఇంటూ ఆర్టీహెచ్ ప్లస్ R2 డాష్ ప్లస్ రూట్ ఓవర్ ఆర్టీహెచ్ ప్లస్ R2 డాష్ ప్లస్ x1 స్క్వేర్. PM max depends on rotor resistance R2 dash whereas TEM does not. At starting internal mechanical power developed is zero. In order to get maximum power output from induction generator, the rotor speed NR equal to NS whole into separate 1 plus 1 separate plus numerator part small R2 dash by denominator part root దీని మాత్రం వస్తుంది దీనికి R2H plus R2 dash whole square plus x1 square దానికి మాత్రం అండర్ రూట్ సెపరేట్గా ప్లస్ స్మాల్ R2 dash I2 ST by I2 whole square equal to 1 plus SMT by S square whole square by 1 plus SMT square. I2 MT by I2 whole square equal to half into 1 plus SMT by S whole square. Where I2 S2 means stator load component of current at starting. I2 comma MT means stator load component of current at maximum torque. Approximate analysis. R2 I2 dash equal to V numerator part V whole by denominator part R1 plus R2 dash by S whole square plus x square under root. Denominator part full ga under root వస్తుంది. Capital T equal to 3V square R2 dash by S whole by దీని అంతటి పార్ట్కి డినామినేటర్ పార్ట్ హోల్ బై ఒమేగా S ఆఫ్ R1 ప్లస్ R2 dash by S హోల్ స్క్వేర్. R1 ప్లస్ R2 dash by S మాత్రమే హోల్ స్క్వేర్ వస్తుంది. ఇదంతా సెపరేట్ ఇప్పుడు ప్లస్ ఎక్స్ స్క్వేర్. స్టార్టింగ్ టార్క్ TST ఈక్వల్ టు 3V స్క్వేర్ R2 dash by ఒమేగా S ఇంటూ R1 ప్లస్ R2 dash హోల్ స్క్వేర్. ఇదంతా సెపరేట్ పార్ట్ ప్లస్ ఎక్స్ స్క్వేర్. Maximum torque TM equal to 3V square whole by omega S into 2x2 dash. Slip at maximum torque SM equal to R2 dash by x2 dash equal to R2 by x2. డయాగ్రామ్ చూస్తాం చూడండి. RC ప్యారల్ విత్ JX5 దాని నుంచి I0 కరెంట్ పాస్ అవుతుంది. దానికి సిరీస్గా R1 ప్లస్ R2 డాష్ బై S x ఈక్వల్ టు x1 ప్లస్ x2 డాష్ హోల్ చేసేస్తే ఆ రెండు షార్ట్ చేసి మళ్ళీ గ్రౌండ్కి ఇచ్చేస్తాం. Input voltage is V bar. Input current is I1 bar. At high slip, that is S equal to 1, T is directly proportional to 1 by S. At low slip, that is S equal to 0, T is directly proportional to S. Suppose if we draw a diagram between x-axis అనేది slip, y-axis అనేది torque T అయితే, then negative part is nothing but 2 by 2 మైనస్ NS అనమాట. ఓకేనా. స్లిప్ అయితే 2 అయితే అక్కడ గ్రాఫ్ వస్తుంది, 1 వస్తుంది, వై యాక్సిస్ దగ్గర టార్క్ వస్తుంది. టీఈఎస్టీ స్టార్టింగ్ టార్క్, అది రెసిడ్యూ ఉంటుంది. ఓకేనా. హై గ్రాఫ్ వచ్చిందంటే బ్రేక్ టార్క్ టీఈఎం అని వస్తుంది. ఫుల్ లోడ్ ఆపరేటింగ్ పాయింట్, ఇంటర్సెక్షన్ బిట్వీన్ ద స్లిప్ అండ్ దిస్ గ్రాఫ్ గివ్స్ యూ నో లోడ్. ఓకేనా. ఇంకోటి ఎక్స్ యాక్సిస్ స్పీడ్ వేసుకొని వై యాక్సిస్ టార్క్ అని వేసుకుంటే సేమ్ గ్రాఫ్ వస్తుంది. అట్ ఆరిజిన్ దెర్ విల్ బి సమ్ టీఈఎస్టీ స్టార్టింగ్ టార్క్, ఎస్ మ్యాక్స్, ఎన్ఎస్ ఒకటి ఇటు సైడ్ ఉంటుంది ఎక్స్ యాక్సిస్, మైనస్ ఎన్ఎస్ అనేది వై యాక్సిస్ ఉంటుంది. మైనస్ ఎన్ఎస్ ఉన్న దగ్గర బ్రేకింగ్ మోడ్ ఎస్ గ్రేటర్ దెన్ 1, 0 to ఎన్ఎస్ దగ్గర మోటరింగ్ మోడ్ 0 less than equal to ఎస్ less than equal to 1. ఎన్ఎస్ టు ఫర్ గ్రేటర్ దెన్ ఎన్ఎస్ జనరేటింగ్ మోడ్ ఎస్ లెస్ దెన్ 0. టార్క్ స్లిప్ క్యారెక్టరిస్టిక్స్ అంటాం. దీన్నే టార్క్ స్లిప్ క్యారెక్టరిస్టిక్స్ అంటాం. Tm is directly proportional to 1 by f square. Tst directly proportional to 1 by f cube. Efficiency of Im, eta is directly proportional to 1 minus s by 1 plus s, where f equal to frequency, s equal to slip. The polyphase induction motors. Okay, determination of equivalent circuit parameters. No load test, OC test. Test performed at rated voltage to determine iron loss at rated voltage, that is Pi, shunt branch parameter, that is RC and XY, where I naught equal to no load current, V equal to rated voltage applied to stator, Pi means fixed losses read by wattmeter, RC equal to V square by Pi, GC equal to 1 by RC, R base C అని వస్తుంది, V square by P suffix I వస్తుంది, G suffix I equal to 1 by R suffix C, Z naught equal to R suffix C parallel with J X naught, Y naught equal to 1 by Z naught equal to JC minus ఏందది Y naught equal to 1 by Z naught equal to G suffix C minus J beta suffix phi, that is called GC minus J beta GA B phi. Y naught equal to I naught by V, B phi equal to root of R Y naught square minus G suffix C square, X suffix phi equal to 1 by B suffix phi. Block rotor test. Supply is given but the rotor is blocked to rotate mechanically. This test is also called a short circuit test to determine copper loss at rated current. This test is performed at rated current condition. ISC means rated current, VSC means voltage that is required to circulate ISC when rotor is blocked. PSC total copper loss on full load at standstill read by wattmeter, R equal to PSC by I square SC. ZSC means VSC by ASC. X means root over ZSC square minus R square. The diagram is resistance parallel with X, where R1 plus R dash equal to capital R. ISC, VSC, X దగ్గర short circuit. In block rotor condition, reduce voltage on brackets up to 5% of rated is required to flow the rated current. Starting method of 3-phase induction motor. Direct online starting DOL. To reduce the starting current if voltage is reduced by fraction x, the starting current is also reduced by fraction x, but the starting torque gets reduced significantly by a factor of x square. Auto transformer starting. Both starting current from supply and torque are reduced by same factor x square. If x equals 1 by root, the results are the same as y to delta starting. Next, start delta starting. In this delta connected induction motor started as Y connected, and as motor picks up the speed, the connection are changed to delta, that is it runs as a delta connected. If delta connected IM is induction motor is started as star connected, both the starting current and torque are reduced by a factor of 1 by 3. By increasing rotor resistance, starting torque increases but maximum torque remains unchanged. Speed control of induction motor. Rotor speed of induction motor is NR equal to NS into 1 minus S. The rotor speed can be controlled by slip control technique and synchronous speed control technique. Slip control technique, T equal to SV square by R, where T is remaining constant. Voltage control technique applicable for both IM, that is slip ring induction motor, SRIM, and squirrel cage induction motor. Rotor resistance method only in SRIM, slip ring induction motor. Rotor EMF injection method only in SRIM, slip ring induction motor. Synchronous speed control technique NS equal to 120 F by P and NR equal to NS into 1 minus S. Frequency control technique application is applicable in both induction motors. Pole changing technique only in squirrel cage IM. Cascading of two induction motor. In this method, one IM must be SRIM while other can either squirrel cage or SRIM. Cogging. COGGA and number of slot in the stator equal to S1. Number of slot in rotor equal to S2. If either S1 equal to S2 are integral multiple to each other, then the stator teeth and rotor teeth, which are actually parallel, may develop very strong alignment, forcing at the time of start, and therefore the induction motor may fail to start. With rotor teeth blocked against the stator teeth, this phenomenon is known as cogging. COGGING, crawling. The air gap flux in a three-phase induction motor contains harmonics of the order of 6n plus or minus 1, then create parasitic torque. Due to this harmonic, motor continues to rotate stably at a speed n much less than the full load speed NFL. N suffix FL, NFL. This phenomenon is called as crawling. Now remember, cogging and crawling phenomena are usually not encountered in SRIM as their starting torque is high enough to accelerate it. Power factor: wide bar rotor less than, deep bar rotor less than, semi-open slot less than, closed slot. Leakage flux: closed slot greater than, semi-closed slot greater than, deep bar greater than, wide bar. Next, the polyphase synchronous machines. A three-phase synchronous machine is a doubly excited AC machine because its field winding is energized from a DC source and its armature winding is connected to an AC source. It rotates with speed of revolving field, that is synchronous speed. In synchronous speed machines, windings are always connected in star, armature winding is placed in stator, and field winding is in rotor. Synchronous speed NS equal to 120 F by P RPM, where F means frequency of armature current, P means number of field poles. RMS induced EMF per phase, EA equal to 4.44 F N base E, N suffix E, NE, phi suffix P, phi P. EA equal to 4.44 F NE, phi P. Where NE means effective turns per phase, phi P means total flux linking a full pitch coil. Effective number of turns, N suffix E equal to N suffix C into K suffix P into K suffix D. N suffix C, NE equal to NC KP KD, where NC equal coil turns, KD means distribution factor, KP means pitch factor, winding factor K suffix omega equal to KP into KD. KP into KD. Types of rotors: silent pole motor, silent pole rotor. Silent pole windings are concentrated windings and connected in series. D axis and Q axis are 90 degrees electrical to each other. Air gap is minimum along D axis and maximum along Q axis. Silent pole machine drives at low speed, hence is called as low speed alternator or hydro alternator. Silent pole rotor has large diameter and small axial length. Silent pole alternator, also called as hydro alternator. Cylindrical rotor. Field winding is distributed in and all coils are connected in series. Air gap is uniform in cylindrical rotor. In cylindrical rotor can be driven with at high speed, so it is also known as high speed alternator or turbo generator. Cylindrical rotor has smaller diameter and larger axial length. In alternator, main field MMF leads the air gap MMF and air gap MMF leads the armature MMF. Therefore, in alternator, main field MMF is most leading. In motor, main field MMF lags the air gap MMF and air gap MMF lags the armature MMF. Therefore, in motor, main field MMF is most lagging. For unidirectional torque production, number of rotor poles must be equal to the number of stator poles and they must be stationary with respect to each other. Now the heading is armature reaction.
The effect of armature flux phi A on main field flux phi M is known as armature reaction. Armature reaction depends upon the magnitude of load and load power factor. Now I will read one by one. Point 1, power factor is unity. The purely cross magnetizing alternator, purely cross magnetizing motor. And the power factor is ZPF, purely demagnetizing alternator, purely magnetizing motor. When the power factor is ZPF lead, previous one lag. When ZPF lead, power factor gives you purely magnetizing alternator, purely demagnetizing motor. When the power factor is 0.8 lagging, then the partly demagnetizing plus partly cross magnetizing alternator, partly magnetizing plus partly cross magnetizing motor. When power factor is 0.8 leading, then the partly magnetizing plus partly cross magnetizing alternator, partly demagnetizing plus partly cross magnetizing motor. Synchronous generator model. EF bar equal to VA bar plus IARA minus EL minus EAR. These are all suffix. EF equal to VA plus IARA plus JXAX1, JIAX1 plus JIAXA. X1 కాదు XL. Here EF means excitation voltage or internal voltage. EAR means armature reaction voltage. EL means armature leakage flux voltage. RA means armature resistance. Then XL means armature leakage reactance. XA means armature reactance. IA bar means armature current. VA bar means terminal voltage. EF means RA. EF की series లో RA, JXL, JXA. The output voltage is VA. That equivalent is nothing but EF bar equivalent is JXS equal to J of XA plus XL in series with RA. Output voltage is VA. EF equal to VA plus IARA plus JIAXS, where XS means XL plus XA equal to synchronous reactance. EF means VA bar plus IAZS. ZS means RA plus JXS synchronous impedance. That is called as synchronous impedance. Drop in voltage, drop due to armature resistance, that is IARA. Drop due to armature leakage reactance, that is IAXL, due to armature leakage flux. Drop due to armature reaction, that is IAXA. The terminal voltage of an AC generator depends upon the load and may be larger or smaller than the generated voltage. The terminal voltage may actually be higher than the generated voltage when the power factor is leading. For unity and lagging power factor, the terminal voltage is smaller than the generated voltage. When EF cos delta equal to VA, normal excitation, brackets so unity power factor. When EF cos delta greater than VA, over excited machine lagging power factor. When EF cos delta is less than VA, under excited machine, bracket lo leading power factor. Next concept is synchronous generator tests and characteristics. Resistance test. Per phase resistance for star connected generator, RA equal to 0.5 RL. For delta connected generator, RA equal to 1.5 RL, where RL means measured value of resistance. Open circuit and short circuit characteristics. For synchronous generator tests and characteristics, open circuit and short circuit characteristics, find the value of field current I suffix FR that gives the rated per phase voltage V suffix ANL from the OCC of the generator. Find the value of the short circuit current ISC from the SCC for the same value of the field current IFR. Field current IF, IF1, air gap line OCC, SCC, then x-axis లో no load or per phase voltage. దానికి y-axis లో ఏం రాస్తామంటే V base ANL, x-axis లో IF1, IFR, field current IF, short circuit current. ఓకేనా. నెక్స్ట్ synchronous impedance. ZS equal to open circuit terminal voltage for a certain field current by short circuit current for the same field current. ZS equal to VANL by ISC. synchronous impedance, unsaturated region, saturated region, field current IF, x-axis లో field current IF, y-axis లో synchronous impedance ZS. Synchronous impedance ZS. Next, external characteristics. External characteristics of synchronous generators and characteristics. Okay na. Synchronous generator short circuit ratio SCR. SCR is defined as the ratio of field current required to produce rated voltage and open circuit to the field current required to produce rated armature current on the short circuit. SCR equal to IF for rated open circuit voltage whole by IF for rated short circuit current. SCR equal to ISC by I rated, that equal to ISC PU. SCR equal to 1 whole by XS bracket lo saturated PU. For hydro generator SCR is high. SCR means short circuit ratio. For turbo generator SCR is low. A synchronous machine with high value of SCR is a better voltage regulation and improved steady state stability limit, but short circuit fault current is in armature is high. A machine with low SCR is less stable when operating in parallel with other generators, but the armature current and the short circuit condition is small. Voltage regulation is defined as rise in voltage expressed as a fraction of full load rated voltage when full load is thrown off while keeping the excitation constant. Regulation equal to modulus of EF minus VA by whole by VA. Regulation is less than ZS. Order of voltage regulation in alternator is 30 to 40%. For minimum voltage regulation, zero voltage regulation is possible only for leading power factor loading. For zero regulation, cos of theta plus phi equal to minus IA ZS by 2V, or theta plus phi equal to 90 degrees, where theta means impedance angle, phi means power factor angle. Y-axis లో XS, Z-axis లో XS X-axis లో RA, దాన్ని పైథాగరస్ థీరం బట్టి ZS. Maximum voltage regulation. Maximum regulation is possible only for lagging power factor load. For maximum regulation, load PR power factor angle phi equal to impedance angle theta. Voltage regulation is always positive for resistive load or UPF load or lagging power factor load. Voltage regulation could be positive for high leading power factor 0 and negative for leading power factor load. Voltage regulation method. Synchronous impedance method, EMF method. Here we assume drop due to armature reaction is considered drop due to leakage reactance. It gives regulation more than the actual value and hence it is called as pessimistic method. MMF method, amp turn method. Here we assume drop due to leakage reactance is considered as drop due to armature reaction. This method gives regulation less than actual value, therefore it is called as optimistic method. ZPF method, plot of VA versus IF corresponding different field current for maintaining rated armature current at zero power factor lag, called ZPF. Characteristics of Portier triangle characteristics. ASA method, here effect of saturation is also considered. This method is combination of ZPF and MMF method. Voltage regulation, EMF greater than ASA greater than ZPF greater than MMF. Two reaction theory. This theory is applicable to salient pole machines only. ID equal to IA sin psi, IQ equal to IA cos psi. Where ID equal to direct axis armature current, IQ equal to quadrature axis armature current. E equal to VA cos delta plus I suffix Q R suffix A, IQ RA అంటుందని, plus or minus I suffix D X suffix D. Tan psi equal to VA sin phi plus or minus IA XQ whole by, దానంతా whole by వస్తుంది, VA cos phi plus IA RA. Psi equal to delta plus or minus phi. Here plus sign for lagging power factor and sign for leading power factor, where psi means internal power factor angle by which IA lags E, delta means load angle between E and V. Phi means power factor angle between VA and IA. If RA neglected as RA far less than XS, ID equal to E minus VA cos delta by XD and IQ equal to VA sin delta by XQ. Per phase power P equal to E VA sin delta by XD plus VA square by 2 of 1 by XQ minus 1 by XD into sin 2 delta. E VA XD sin delta is the electromagnetic power. VA square by 2 into 1 by XQ minus 1 by XD sin 2 delta is called reluctance power. In cylindrical rotor, P reluctance is 0 since it does not have Sal C, and XD equal to XQ equal to XS. Reluctance power is generated only when machine is connected to or operating on infinite bus bar.